One question almost immediately comes up about a convergent sequence and its limit. How do they relate? How does the limit of a sequence relate to the sequence itself? For example, if a sequence like this one here is always positive, does that mean that the limit is always positive? One that is always greater than the other, so a sub n is greater than or equal to b sub n. Does that mean that their limit is always greater than or equal? If we have a sequence that's bounded by some value, like in this case 3.5, if all of our terms in our sequence are less than 3.5, does our limit have to be less than 3.5? We have an answer in the form of a very important theorem in real analysis. I'll call it the order limit theorem. Sometimes you might see it as the sequential order limit theorem, because later on we'll talk about limits in terms of functions, not in terms of sequence. However, for the sake of right now, we'll call it the order limit theorem. And there are actually three parts to this theorem. I'll prove them in order. That's why two of those parts you'll see are kind of the same. The first part is, well, let's say we've got a sequence. Before I give you the theorem, let's say that we have a sequence a sub n that converges to a value a. And let's say we got a sequence b sub n which converges to b. We can apply the theorem as shown. The first part is, for all natural numbers n, if a sub n is greater than or equal to 0, that is, if all of our terms in our sequence are greater than or equal to 0, then the limit is greater than or equal to 0. Secondly, we'll prove that for all natural numbers n, if a sub n, our sequence a sub n is greater than or equal to b sub n, then the limit values, limit of a sub n, is also greater than or equal to the limit of b sub n. Finally, we'll generalize part 1 of the order limit theorem to tell us that for all natural numbers n, if a sub n is greater than or equal to not 0, but let's say any number c, where c is any real number, then our limit is also greater than or equal to c. And you could probably guess that what happens if a sub n is less than or equal to c? Well, our limit is less than or equal to c. What will happen, as I'll show, is this first part is fairly easy to prove, but even more interestingly, the second two parts, are incredibly easy to prove once we've shown this first part. Well, let's look at this first part. This is saying that if a sequence is always greater than or equal to 0, if it's always non-negative, then the limit is non-negative. I've graphed ourselves a sequence here that is, as you'll see, non-negative, and the limit is 0, which is also greater than or equal to 0. And let's, by proof by contradiction, show that it can't be the case that our limit were negative. So, for instance, it cannot be the case that a is less than 0. We'll prove this by contradiction. So, suppose this sequence, which is always positive, converges to a low value down here. There's our little a. A is living down somewhere below the x-axis, or I guess in this case it's the n-axis, but whatever. In that case, by the definition of convergence, because we're assuming a sub n is converging to just the value a, we can make a sub n arbitrarily close to a. What does that mean? For all positive epsilon, there's a term in our sequence n such that for all subsequent terms little n, subsequent meaning greater than our nth term, a sub n minus a, the distance between a sub n minus a, absolute value, is less than epsilon. We can make this arbitrarily small using that epsilon value. Let's make a little neighborhood, an epsilon neighborhood about our limit here. And let's make it small enough so the whole thing is also beneath our n-axis, our x-axis. So, for example, we could consider we let epsilon be the absolute value of a over 2. This will guarantee if we use this length, absolute value of a over 2, this length away from a, that means we've got this region. We've got this region here that is always below the x-axis. Since a sub n converges to a, for this choice of epsilon, we can find a term in our sequence n such that all the other terms are this close, epsilon close to a. Graphically, that means we should be able to, sometime in our sequence, find some term n after which all our other terms are this close to a. We have found that, well, we're eventually going to have to be negative. If our limit value here is negative, there are going to be actually an infinite number of terms that are also negative below 0. That contradicts our assumption that our sequence was fully positive. In other words, for our limit to be negative, our sequence, no matter what you choose for a, will have to eventually become negative at some point. That proves part A. Let me clear some space so we can prove part B, which is incredibly easy given part A. It's a little trick that I'll show you. So we prove part 1. We'll use part 1 to prove part 2. Let's rewrite our assumption right here, that a sub n is greater than or equal to b sub n. To use part 1, if we're really clever, we could subtract b sub n to get a similar inequality. We have some sequence that's greater than or equal to 0. And look at this. This itself, we could define this as its own sequence. We could consider this its own sequence. Since this sequence is always greater than or equal to 0, by part 1, we know that the limit, we're assuming that our sequences converge to a and b, as I did up here. We know by the algebraic limit theorem for sequences that the difference of limits is the limit of differences. So in other words, a sub n minus b sub n, and you could probably intuitively guess this, converges to a minus b. By part 1 of what we just proved, this is greater than or equal to 0. We'll add b to both sides, and voila, a is greater than or equal to b, thus proving part 2 of the order limit theorem. Lastly, we'll prove part 3. What we can do here is just say that b sub n is just some constant c, some constant sequence c. What do I mean by that? This is just some sequence. We have c, 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 and so on. Using that fact, we can employ part 2. By part 2, we know that for all natural numbers n, a sub n is greater than or equal to c. This is the exact same thing as saying a sub n is greater than or equal to our b sub n sequence. By part 2, b sub n clearly converges to c. Nothing's changing there. So our limit a is greater than or equal to c. And we're done. By replacing this constant c here with a sequence of just c, we're able to take part 2, throw it in there, and get a nice clean answer. What's especially interesting about the way this order limit theorem unveils itself is once you've proven part 1, it's incredibly easy, once you prove this part 2, to generalize part 1, not just talking about this number 0, but to talk about any real number c. When a sequence, all the terms in the sequence are bounded by something, either above or below, that limit is consequently bounded. This is a critical property, a critical relationship, similarity between sequences and their limits, and this will show up throughout real analysis. But thanks for watching.